Welcome to Math 408, L functions and sphere packing. This is lecture 12 on Dirichlet's theorem in Fourier analysis. We have to be a little careful and say in Fourier analysis because Dirichlet has quite a few theorems to his credit. So we want to start by just reviewing a little bit of what we did last time. So we saw that there are two very useful functions in studying Fourier series and Fourier analysis. And the first is the Dirichlet kernel, dn, which is defined as the sum of the exponential function. En is e to the 2 pi I n x, going from minus n to n. And it has this nice formula where it's a ratio of 2. And we have similarly a weighted sum of these Dirichlet kernels, which is the Fourier kernel, which is going to be a ratio of squares of signs. And the fact that the second one is squares has a lot of very nice properties. In particular, it means that it's an approximation to the identity, and we got Fourier's theorem, which we'll talk about shortly. So your first homework assignment is to actually prove these two formulas for dn and fn. And the strong hint is the geometric series almost surely is going to be helpful, given that this is actually a geometric series itself with ratio e1 of x. And so last time we proved Fourier's theorem, and to just point it out in its full glory, if we take a continuous periodic function on 0, 1, then no matter what epsilon you give me, there is some n naught such that for all n greater than n naught, the difference between fx and the Fourier series, Tn of x, is less than epsilon. And this holds for all x in the interval 0, 1 simultaneously. So this is the great uniformity. We don't have to do a different n for each x. Thus, in particular, as n goes to infinity, Tnf is going to converge pointwise to f of x at a nice rate we can control. And the starting point in the proof was multiplying by 1 in a very clever way. And this is an extremely common technique that occurs again and again and again. And because our functions integrate to 1, and we can see that because of these ens, every one of these ens integrates to 0 if n is not 0, because it's going to be cosine plus I sine. But if n happens to be 0, then e0 is just 1, and when we integrate 1 from 0 to 1, we just get 1. Over here for the Fourier kernel, each one of these dn's integrates to 1. We have n of them, we divide by n, so it still integrates to 1. And so that was the starting point, is we multiplied f of x by this integral representation of 1, and that allowed us to combine things. So a couple of definitions and some remarks. So a trigonometric polynomial is a finite linear combination of the enx's. If you expand this out, it's going to be sums of sines and cosines to different periods, all integer periods. And from Fourier's theorem, we immediately get a beautiful result due to Weierstrass that any continuous periodic function can be uniformly approximated by trigonometric polynomials. So this, many different ways to prove this. The different ways have different generalizations. As a nice exercise, 11.3.6, prove the Weierstrass approximation theorem implies the original form of the Weierstrass theorem. And so, again, we're assuming by here the Weierstrass approximation theorem that we have a function that's continuous, periodic, can be uniformly approximated by trig polynomials. Now we want to prove that it can be approximated by just a regular polynomial in x. Okay, so just setting some stage before we do Dirichlet's theorem, the nth coefficient, the nth Fourier coefficient is f hat of n. It's obtained by integrating f of x against e to the negative 2 pi I n x. And we can form the finite Fourier series approximation by just summing from minus n to n of f hat of n times e to the 2 pi I n x. So we view these almost as our vectors, our basis vectors, and this is the projection of our function in that direction. As a nice exercise, and I believe we did this last time, you can show that we can get this finite Fourier series by taking the convolution of our function f and the Dirichlet kernel. And so Dirichlet proved the following wonderful result. So assume f is real valued, periodic with period 1, its absolute value is bounded, and assume it's differentiable at a point x naught. Then the Fourier series converges to the value of the function at that point x naught. And it should always be the case whenever you have a result in real analysis, you should ask, what happens if we weaken some assumptions? What if f was complex value? Would this still be true, for instance? What if f is not bounded? What if it's bounded near x naught? Well, has to be bounded near x naught, of course, because it's differentiable there, but what if it's unbounded elsewhere? Would the result break down? And of course, think about these things as we go through the proof. So we start with dn as the Dirichlet kernel. We show that it equals this nice ratio of signs. And we know that the Dirichlet kernel integrates to 1. So we do the same trick as before. We look at f of x minus Sn of x naught. We write f of x naught as f of x naught times 1 in an integral form, and we write the Sn of x naught as the convolution of f in the Dirichlet kernel. And the reason we do it this way is because now both of the expressions have an integral against dn of x. Well, that's great. We can bring this inside the integral because this has no x dependence, and we get f of x naught minus f of x naught minus x. Okay, so as long as we stay away from x naught, this is going to be nice. When x gets near, sorry, as long as x stays away from 0, this is going to be nice. When x is 0, we have f of x naught minus f of x naught, which is 0. So that can actually cancel some problems over here in dn of x if we have that. But a better way of looking at it is, because this is going to 0, we could actually divide this by x and we would still be okay. And that's what we're going to do, because we're going to write the Dirichlet kernel as a ratio of 2 signs. And when x is very close to 0, the sign of pi x is approximately pi x. So it looks like 1 over pi x in the denominator here. So if we put the sign of pi x over here, this is kind of looking like a derivative of my function at the point x naught. And then this part over here is nice and well behaved. It's bounded by 1 in absolute value. It's continuous. It's differential. So let's call this function over here g of x naught. And we're going to put the x naught in the name of g to remind ourselves that it's coming from this point x naught. And so we want to take this integral, and we want to show that this integral is small. And so the first thing is we claim that g of x naught is bounded. So as f is bounded, okay, we're beginning to use that assumption now. We know that the numerator is bounded. The problem is the denominator can get very small as x gets closer and closer to 0. And that's where we need to use the differentiability. Because the function is differentiable, if we multiply by x over x, well, the x over sine pi x is going to converge to 1 over pi by L'Hopital's rule. And then this is going to look like the derivative. It's going to look like f prime of x naught. Since the function is differentiable, if x is sufficiently small, we can make this ratio as close as we want to f prime of x naught in absolute value. So again, we can do this by just multiplying by 1 in a clever way. We'll multiply by pi of x over pi of x. So this by L'Hopital's rule is just 1. This is going to go to f prime at x naught divided by pi. So g is bounded everywhere, let's say by b. As g of x naught is a bounded function, it is square integrable, and thus by the Riemann-Lebesgue lemma, its Fourier coefficients tends to 0. So now this is something that's a little bit interesting. We need some control over the Fourier coefficients. What is necessary for this to be the case? And so if you look at what we're assuming, we're just assuming right now that our function is bounded. So that means it's an L1, that means it's an L2. And if it's an L1 and L2, then we're in pretty good shape. So we remarked that we're using now the Riemann-Lebesgue lemma that the Fourier coefficients tend to 0. Because essentially, that's what we have here. When we look at what we have g of x naught times this. That's just the imaginary part of the Fourier coefficient. And now that would be at negative 2n plus 1 as the argument. So why is this the case? Why do the coefficients tend to 0? Well, it's a bunch of useful properties, and some of these we've proven, some of these we've almost proven. So using the inner dot product, we know if we take f of x and subtract off its finite Fourier approximation, then its projection in the direction of en is 0. We know each Fourier coefficient is at most the L1 norm, so if our function is bounded, we know f hat of n is bounded. It exists, well then. We have Bessel's inequality, and so this is if the L2 norm is finite, then the integral of f hat of n squared is less than or equal to the inner product of f with therefore the L2 norm. And because we're assuming our function is bounded, then its L2 norm is finite. And so we showed that if you just sum from any maybe minus big N to big N, that's going to be less than or equal to the L2 norm. So letting big N go to infinity, we get Bessel's inequality. And so once we have this, the only way that this sum can be finite is if the terms go to 0. And so Bessel's inequality immediately implies the Riemann-Lebesgue lemma. Now, we proved the Riemann-Lebesgue lemma through Bessel's inequality, which assumes that our function is square integrable. It turns out the Riemann-Lebesgue lemma is true in greater generality you only need to assume that the function is an L1, that the integral of the absolute value of f is finite. So a good problem, or good thing to try to investigate is, how much can you weaken what we're doing? Can we still prove Dirichlet's theorem if we assume maybe some L1 results? And we have to be a little bit careful now because we were using boundedness, but how is boundedness really being used? Can we avoid that? And then the last remark, which we've seen before, is that the more differentiable you are, the smaller your function is, the more decay you have in the Fourier coefficients. So the Riemann-Lebesgue lemma just says they go to 0. It doesn't say anything about the speed. And what point 5 says is that if you're differentiable, decay at least as fast as order 1 over n to the k. And the constant is going to depend on, not surprisingly, the function and all of its derivatives up to the k. All right, so returning to what we have, we know that g of x naught is nice. It's a bounded function. It's square integrable. So we can use the Riemann-Lebesgue lemma. So this goes to 0. And if that goes to 0, well, if we just return to what we were looking at, we had a function minus the approximation, and that was equal to this integral of g against the sign, which is essentially just the Fourier negative n plus 2n plus first coefficient. And so since that's going to 0, this difference is going to 0, and that means we have convergence. And that finishes the proof of this Dirichlet's theorem. So just as a remark, if f is twice differentiable, we now know that the coefficients are decaying at least as fast as 1 over n squared, and then that means the series should actually have some good convergence properties. So again, we just said that the series converges. We don't know anything initially about how well it converges, how quickly. As remarked in last class, strange stuff can happen. So it's possible for the Fourier series of a continuous function to diverge at a point. Kolmogorov in 1926, constructed a function that has a finite L1 norm, and the Fourier series is diverging everywhere. But if the L2 norm is finite, the story is completely different. Carlson was the first to prove that the Fourier series converges to the original function almost everywhere. Charlie Fefman also has a nice, beautiful proof of that. So as another homework problem, let's do exercise 11.3.10. You have probably figured out that these screenshots are coming from some book. This is a book I wrote a few years ago when I was a postdoc at Princeton and then Ohio State and then Brown on guided undergraduate research. This is an invitation to modern number theory with my colleague and friend Ramin Taglubikesh. And so the question is, let's say we know f hat of n is 1 over 2 to the absolute value of n. Does this Fourier series converge to a nice continuous differentiable function? If so, is there a simple expression for that function? And that is it for this lecture. Have a great rest of the day. Take care.